We have been talking about acids and bases. And I think I brought up this generic reaction on Friday, which was the acid Ha reacting with a base to make some protonated base and a conjugate acid. Let me show you some examples because I think so this is a continuation of 2.7, still going. Pretend like this is me just picking right up from Friday. You're gonna have to use your imagination because I'm not doing a very good job of that right now. I think having generic acids and bases react is kind of too out there. So let's use some specific examples. You can use something like HCl. You might know that HCl is a common acid. It is hydrochloric acid. In Gen Chem, you may have been made to memorize a few strong, what are called mineral acids. So things like sulfuric acid, nitric acid, hydrochloric acid. These are ones that when they show up in a reaction, they're always going to give off a proton, right? And remember, a Bronsted-Lowry acid is a molecule that gives up a proton. So we're going to react it with water. Each. And it's going to form an equilibrium. So if HCl is acting as my acid, then water is going to act as my base, which means HCl better lose a proton and water better gain a proton. If HCl loses a proton, it's going to turn into Cl minus. And I will call that now my conjugate base. Because remember, an acid turns into a conjugate base. H2O took on a proton to become what? H3O. This is a molecule we're going to see a lot in this class. So water had two lone pairs. Now it's got one lone pair. Where did the other lone pair go? It formed a bond. Any charges present in this molecule? On the oxygen, what is it, Evan? A positive one. Thanks. Body, how'd you get to that? So you were looking at the periodic table or thinking about, hopefully, has everybody got this down that knowing 3, 4, 5, 6, 7, boron, carbon, nitrogen, oxygen, fluorine, if you can get that memorized, your life's much easier, right? We use it a bunch in here. So I think it's helpful. Body was thinking about, and Evan were thinking about the valence electrons that oxygen should have. That is 6. It has 1, 2, 3, 4, 5, which means the oxygen has a positive charge. That means that I've turned my base into a conjugate acid. This one in particular, I want you to know the name of. This is called hydronium. Anytime we have a positive charged ion, or what we call a cation, we normally give that an -ium ending. Right? So if I put a positive charge on an oxygen, it's broadly called an oxonium ion. When I have this particular setup with an O with 3 hydrogens, it is a hydronium, so that is water with a positive charge. The hydronium ion will be used a lot in here. So that's one example of an acid-base reaction. Let me show you another one, though, because it's not always straightforward about which molecule is your acid and which one's your base. If I give you these two molecules, so now I've got water. And does anyone know what this molecule is? NH3? Smells real bad. What? Ammonia? Anybody got cats? Smells like cat pee. So good. So good. This is why you don't clean your litter box with bleach. If you mix ammonia and bleach, you make chlorine gas. And then you, what's that called? Die really painfully. Right. So don't clean out your litter box with bleach because cat pee is made of pretty much ammonia and then some other stuff, but that really strong, horrible scent is ammonia. I'm going to stop talking about cat pee now. Which one of these things, the cat pee or the water, is going to act like an acid or a base? It's not super clear. I will tell you that this is going to act as my acid, and this is going to act as my base. And you may be wondering, well, how did you know that? We're going to talk about it in just a second, how I can numerically figure this out. But if I told you, since I've told you that that's the acid and base, let's see if we can predict the products that we're going to form here. What is my water going to look like on the other side of this reaction? An OH, any charges? a negative charge. So it lost a proton and the electrons went onto the oxygen, so it turned into an OH minus. That was an acid, so it turned into a conjugate base. And then somebody else, what's going to happen to my ammonia? The nitrogen's going to gain a proton. Who was that? Grace? And what's that going to turn into? NH4. Any charges on that? Oops. Any charges on my NH4? It's positive. That is going to be my conjugate acid. You may be familiar, I'm not going to have you memorize this, but you may be familiar with that term. When ammonia takes on a proton, it turns into ammonium. Right? So you've probably heard both those words. Ammonia, like Windex is an ammonia cleaner. Ammonium, if it's got a counter ion, like ammonium hydroxide is one that's commonly used. Also in a medical setting, ammonium hydroxide shows up. Another example of an acid-base reaction. Something gave my acid, lost a proton. It was H2O, now it's OH. My base gained a proton. It was NH3, now it's NH4. Bronsted-Lowry acids lose protons. Bronsted-Lowry bases gain protons. Easy enough, right? Now predicting products, not so easy. Knowing what an acid generally is and what a base is our base level, or basal, is our ground level knowledge. Being able to predict a reaction is the hard part. So let's talk about how we're going to do that. And I think water is a great example for this because up here, water acted as a base, and down here, water acted as an acid. So depending on what it's reacting with, water can be either one of these species. What, my group of nerds, is that called? Who paid attention in Gen Chem? Yeah. It's right there. Just amphoteric or amphiprotic is also the way that you would normally say that. Right? So that it can either take or give a proton. Many molecules can be amphiprotic. They can do both things. Well, because they take on, so water, the oxygen can take on a stable negative charge. It doesn't like having a positive charge, but it can hang on to it well enough. Right? So these molecules that are kind of in the gray area can go one way or the other. So we need to figure out, how can we tell if a molecule is going to act like an acid or a base? Chemists, especially organic chemists, will typically do this from the lens of an acid, but I'm going to tell you in advance, the thing that's going to confuse the crap out of you for the next 30 minutes, 25 minutes, is you can think of this in terms of the base strength or the acid strength, because there's a complementarity to them. If you are a strong acid, you are a weak conjugate base. If you're a strong base, you're a weak conjugate acid. So I'm going to show you how to think about this in terms of both directions. These lines connecting these two things are going to matter to us. First up, one of the ways that we can do this that's probably the most straightforward is to quantify it. So let's talk about acid strength. We'll go back to our generic reaction here, where our generic acid HA is going to react with, instead of writing a base, I'm going to write just water. Our acid is going to lose a proton and turn into A minus. H2O is going to gain a proton and turn into what? Hydronium. Wondering why I just said it like that? To me, hydronium sounds like something that the bad guys in Transformers are trying to get. Hydronium just has this like really hardcore name in my head. That's because I'm a weird person. I can quantify how well this reaction works through the acid dissociations. I'm going to do, heads up, a little bit of math, just like this much math, but not very much. I can use the Ka, which is the acid dissociation constant. And then we will talk about pK as well. Constant. Threw that way too close. Which is equal to what over what? If you ever get lost in chemistry and you've got to divide two things by themselves, what do you always put on top and what do you always put on bottom? Products over reactants. If you are asked to come up with a reaction that you have to cover with math and you were lost, just write the word product over reactant. You'll probably get a point or two because you're probably right on some level. In particular, we're going to put these in square brackets. What does it mean when I put something in square brackets? It means the concentration of that thing. So this is the concentration of the products. This is the concentration of the reactants. The concentration of my face. Anything you put in square brackets means the concentration of that thing. For us, that means we're going to put the concentration of A minus times the concentration. So we multiply these of H3O plus divided by the concentration of our generic acid, HA. Anybody see anything missing from my Ka? Yeah, water. Did I screw up? What is the concentration of water? Does not compute, right? In my coffee cup, I can tell you the concentration of the coffee in here. It's a bit too high today. I can tell you the volume of coffee in here, but what I can't tell you is the concentration of water. We do not put liquids or solids into equilibrium reactions because the question, what is the concentration of water, does not make any sense. I can tell you the concentration of salt in water. I can tell you the concentration of coffee molecules in water, but water itself is the solvent dissolving other things. Water is measured in volume, not in concentration. So no liquids or solids in equilibrium equations. This doesn't apply just to Ka, it also applies to KEQ and a bunch of other reactions you've seen that we're not going to use just yet. Does that make sense, everybody? Is that a yes or I heard a no? Think of it in terms of, I think the ocean's a good example. What is the concentration of water in the ocean? I don't know. There's a bunch of water in the ocean. What's the concentration of the salt in that water? I can measure that and tell you how much weight of salt is in a particular body of water. These numbers get stupid big because what we're going to do is measure the overall concentration of the products divided by the overall concentration of the reactants. And if this number is really, really big, meaning there's a bunch of products, and this number is really small, meaning the reactants all turned into products, then the Ka can get into like the billions and billions and trillions. So we have to use scientific notation for that, and it's annoying. So we are going to use not the Ka, but someone said it earlier, the pKa. The pKa, and that's a capital K, is equal to what? The negative log of the Ka. Don't get too fancy on me here. Okay. I have made this abundantly clear, but I will reiterate this. I know very shockingly, I have a PhD, but I know shockingly little about math. But here's some things that I know. A negative sign means that things get all inverted, right? So the negative here means the smaller the pKa, equals larger Ka. What does a larger Ka mean for acid strength? If you have a big Ka value, are you a strong acid or a weak acid? You are a strong acid, right? You are Woodstock level strong acid. One of us is old enough to know what I'm talking about here. The acid falls apart. So if the acid is any good at giving off a proton, it is going to donate that proton and turn into products. That means that the product's value is going to be very large, and there won't be much of my generic acid down here to divide it by. If this is a strong acid, it means all of my HA reacted and went away. big number divided by small number. Strong acid did that. If this acid doesn't fall apart, right? Water runs into it and water's like, hey, HA, can I have a proton? And HA goes, no, you can't have a proton. This is my proton. Then I form almost none of these products. I have a very small number on top and a very big number on bottom. Small numbers divided by big numbers make really tiny numbers, right? Decimal places. So the bigger the Ka, the stronger the acid. The smaller the pKa, the stronger the acid. Why did we choose to put a negative in front? I don't know. I think it's mean-spirited. But as the pKa goes down, the acid strength goes up. And then the other thing I know is that log makes big numbers small. So if I walked in normal integers, I would say this is 1, 2, 3, 4. If I walked in log, I would say it was 1, 10, 100, 1,000, 10,000. It gets out of hand in a hurry, right? So log is a way we can take these huge numbers of the Ka, which are unwieldy, and unwieldy, they're too big, and we can make them small with the log here. That makes sense? As the pKa goes down, the acid strength is going to go up. So let me show you an example. I'll draw another table here. Names. I have 3 examples. 3 categories here. I'm so good at drawing tables. Look at me go. I'll have an acid over here, the structure of it, the name of that, and its pKa. Let's start with water. That is H2O. The pKa of water is 15.74. That's a number you do not need to memorize, but I want you to be able to compare pKa's. Let's compare that to another molecule that looks like this, which is called acetic acid. Anybody ever heard of acetic acid? Only nerds call it acetic acid. Everybody else calls very dilute solutions of acetic acid vinegar. Do we think that acetic acid is more acidic or less acidic than water? More. What gave it away? Right? Acid's in the name. So acetic acid is more acidic than water. We'll talk about why here in a second, but it has very much to do with the structure. Will that make the pKa of acetic acid higher or lower than water? Lower. The number for acetic acid for its pKa should be lower because it is a stronger acid. If that is true, it is 4.76. Which I want everyone to go, ah! You're doing it over there. It's a yawn, but really it's a gasp. These numbers are very different. I know that 15 and 4 don't seem that far apart, but remember, that's 11, not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That is 1, 10, 100, 1,000, 10,000. I don't know what 11 zeros is. Do I know what 11 zeros is? It's a lot. 11 billion. This molecule is dramatically, shockingly more acidic than water. A pKa difference of 11 integers is huge because that log amplifies the difference between these two. If water and an acetic acid are competing to give away a proton, no contest. It's me running against Usain Bolt. I'm not even going to try, right? If we take this all the way to something like HCl, that is hydrochloric acid. Well, now that I've invoked Usain Bolt, I don't even know, because this is actually going to be Usain Bolt, the fastest, baddest acid on the planet. Pun somewhat intended. Do we think the pKa of hydrochloric acid is higher or lower than acetic acid? Lower. Hydrochloric acid is absolutely a stronger acid than acetic acid. Hydrochloric acid doesn't actually even have a pKa, because to have a pKa means there is an equilibrium, and this doesn't form an equilibrium, but it is considered to be about -7. Once again, shock. That's huge. If I mix HCl with anything, it's given away that proton instantly. None of the HCl is going to sit back here in that form. If HCl can touch anything, it's going to give it a proton, which is why you do not want to get HCl on your hand, because it'll protonate everything it touches, including all the very sensitive skin molecules and everything like that. Lower pKa, stronger acid. Cool. So cool. Okay, so knowing the pKa can let you know which thing is going to act like an acid or a base. There's like a trillion molecules on the planet, so just memorize all those pKa's and you'll be good to go. And that's the rest of this class. Just memorize a list of numbers. Of course, I'm kidding with you. I don't need you to memorize a bunch of pKa's. If you're given pKa's, I need you to be able to use that information. That's more important. You have Google. I also have Google. You can Google pKa's of molecules. I don't need you to memorize all of them. There are many that I don't know. Let me show you different ways that we can play with this if you don't have the pKa, though. Because there is this interplay between acid strength and, well, acid and base strength. So it won't always just be a number that you're given. I'm going to go a little bit out of order here, though. Here is a reaction that I could give you. This molecule is called acetylene. So if you've done any welding and you've ever used an acetylene torch or an acetylide torch, this is one of the tubes that you have coming out. You mix it with oxygen, strike a match, and use a striker. It makes a very hot flame and it's very good at cutting steel. Acetylene can react with this. It's called hydroxide to make acetylide anion and water. Give you some information here. Acetylene has a pKa of about 25. Water, I told you, has a pKa of about 15.7. I have two questions for you. Which species is a stronger acid? Question 1. Is it acetylene or water? Water, because of your fine deduction skills. So kind of why do you say water is the stronger acid? Yeah, so water has a lower pKa, which means water must be the stronger acid. Challenge 1, overcome. There's got to be a follow-on question, though, because that's too easy. Question 2, does this reaction proceed as written? So if I was hired from a chemical company and they're like, Green, because it's probably some mean boss, Green, get in there and mix acetylene with hydroxide. I need that reaction stat. I would say, oh, yes, sir, I'm brand new and I want to make you happy. And so I don't get fired. Am I going to get fired? Oh, yeah, definitely getting fired. Why? This reaction does not work because I'm asking an extremely weak acid to react to form a stronger acid. Well, acetylene doesn't want to lose a proton to turn into acetylide because acetylene is not nearly as strong of an acid as water is. Water can lose a proton to acetylide and go this way. Right? The reaction favors this direction. The stronger acid is going to react to turn into the weaker conjugate base or weaker conjugate. The reaction is going to go this way. Does the reaction proceed? This is really meant to be as written. No. The reverse reaction is favored. I am not going to lose a proton from acetylene to make water when water is the stronger acid. Does everybody see the mental gymnastics we have to go through here? We have to figure out what this is going to turn into and who's going to gain the proton. I am asking a weaker acid to form a stronger acid. Doesn't react that way. Stronger acids will react to form weaker acids. Yeah. Yeah, so another way of putting this is the energy is always going to go downhill. So I am asking a more stable molecule, well, a more stable set of molecules to make a less stable set of molecules over here. Because this molecule having a pK of 25 means this proton does not want to leave. So I'm saying, acetylene, take the hit for me here, lose a proton so I can make water. And water's like, well, bro, I can lose a proton just fine, right? I have a pK of 15, no problem to turn back into hydroxide. I'm sure water speaks in Dubro form. So we have to be able to compare what is losing a proton, what does it turn into, and what would the reverse reaction be? Because these equilibrium arrows really do matter for acid-base chemistry. Let me show you another one. Everybody on the first one was like, yeah, water, crushed it. And then the second question, you're like, no, please, let's go back to the first one. I like comparing numbers. This one's even worse. A molecule called amide. Ooh. That's amide, is a stronger base than hydroxide. Which is a stronger acid. Water or ammonia? Bless you. Any takers? Water. Why? That's right. So hydroxide isn't very good at taking a proton, which means this molecule is stable enough for water to form hydroxide. NH2 minus is very good at taking protons, meaning once it forms, it goes, oh, this is not good. I've got a negative charge. I better grab a proton as soon as possible. A strong base makes a weak conjugate acid. A weak base makes a strong conjugate acid. I will write that down. But water is a stronger acid because of that. Where's our sagely advice going to be? Strong bases form weak conjugate acids, and vice versa. If you are good at giving up a proton, you are not also good at taking a proton on the other side, right? I was good at giving protons away. Think about this with money. You are either a spender or a saver. It's just how people break down, right? You either are really good at buying stuff or you're really good at saving stuff, but you're not typically good at both of those things. For those of you who have found that balance, I congratulate you. I am a spender and I will pay for that for the rest of my life. I am really good at buying stuff. I have a meager savings account, right? Some of you have a great savings account and you're much more responsible. I have more fun than you do. I'm going to pay for it later on in life. If I am good at giving up a proton, I am not good at taking protons on the other side. If I am a strong base, I make a weak conjugate acid. Does everybody see the impending word puzzles coming your way about acid-base chemistry? Okay, so we can do this either by being told what is the stronger acid or base. We can do this by figuring out the pKa or being told what the pKa is. My favorite possible way to do this, though, is to analyze the structure. So really where I want you at, because this is all, if you look back over Gen Chem notes, or if you think hard about that horrible Gen Chem experience, you should have been doing this kind of level chemistry there. Where I want you guys to be able to get to is to look at structure of an organic molecule and predict its acidity. So to do that, let's use some common organic acids. And I will tell you in advance, again, for more word salad coming your way, or more puzzles, that when I ask you about acids, when anybody asks you about acidity, they're not asking you to look at the thing and go, a strong acid or a weak acid. That looks pretty nice, right? What you're really asking is, once you lose a proton, when my acid has a proton taken away from it, what does it look like on the other side? Someone asks you about acid strength, they're really asking you about conjugate base stability. Strong organic acids produce stable conjugate bases. Go back to the coffee cup example. If you take my coffee cup from me, good luck. But I'm going to get to a place, I'm going to fight you for it. You're probably going to win because I'm not very strong. But if you take my coffee cup away from me, I now feel out of sorts. I'm not happy about the situation. So I'm going to go right back over here and take my coffee cup back. I am a weak acid because I don't want to give up my proton. If I didn't have a crippling addiction to caffeine, I could put the proton away and go over here and go, fine, no problem. I'm really good at donating that proton. So what you need to look at is, how am I absent my proton? If I'm stable, I was a strong acid. If I am unstable, I'm going to go right back over here, take the proton back. I am a weak acid. Does that make sense to everybody? As far as my caffeine addiction? I like how I'm like cradling this coffee cup. Let me show you what that looks like for an organic structure. Acetic acid is one I brought up earlier. It looks like this. If I mix acetic acid with the base, let's not worry about what the base is, but something that can take protons. My acetic acid will lose a proton, that one. And it will form this molecule, which I'll show you is called acetate, but I don't expect you to know that just yet. The ate ending is typically how we refer to negatively charged ions, or what we call anions. So I want to know about the acid strength of acetic acid, but to do that, I can't just look at acetic acid and go, is that unstable? Is it stable? Everybody has an octet. Everybody's neutral. It's hard to tell anything about the acidity from just looking at this molecule. So let's take a proton from it and see what it looks like on the other side. How do we feel about acetate? Love it? Hate it? Don't hate it? Don't love it? What do you like about it, Kylie? Yeah, so we've got a negative charge. Don't like that, right? That's not good. But we put the negative charge on an oxygen, so that's pretty good. Everybody's got an octet as far as I can tell, so that's not too bad. We're kind of, Is there anything else about this molecule? Anything else about this molecule? The charge. Resonance, right? It has resonance. The negative charge isn't. I was going to let that go for a while, and everyone was like, "What is he having a stroke right now? What's happening?" The negative charge isn't stuck on this oxygen. I can move it back and forth. And despite the fact that our professor's crazy, we like resonance. Because the negative charge isn't stuck just on this oxygen, it can go up to the top oxygen as well. Let's compare that to another molecule that has a oxygen in it. Methanol. If I mix methanol with a base, again, I won't get so caught up on what the base is because I'm wondering about acid strength here. The OH would lose a proton and it would turn into this molecule, which is called methoxide. Again, don't get too caught up in these names. We'll learn more about these later on. Let's do the same thing. Tell me about methoxide. Why is it worse than acetate?
Negative charge can't move off that oxygen.
Fantastic. We've got a negatively charged oxygen up here. We've got a negatively charged oxygen down here. Everybody has an octet up here. Everybody has an octet down here. Apples to apples, they are the same anion. But this negative charge can move. This negative charge can resonate back and forth between these two structures. There is no resonance down here. What do you think that means for the pKa's of acetic acid versus methanol? Which one of these molecules, acetic acid or methanol, is a stronger acid? Acetic acid is a stronger acid because it forms a stable conjugate base. Methanol does not form a stable conjugate base, which means it's a weaker acid. The pKa of acetic acid is 4.76. Is the pKa of methanol higher or lower than 4.76? Higher. It is 15.54. Does everybody see a question coming their way where your mean, small, black-hearted professor gives you two different structures, doesn't give you the products, has you predict the conjugate base, has you talk about the stability of that conjugate base, maybe gives you a bank of numbers to use to describe the two, and then asks you which one's the stronger acid and what would their associated pKa be? Everybody feel that question coming on? Because it's coming. Because I'm a broken record and it's like the perfect question to be able to ask people. You all look like you could use some more practice with this. I invite you to come hang out with me and all the coolest kids at NSU in 10 minutes in room 248 on the second floor for our action center. Otherwise, I will see you all on Wednesday. Have a good one.